Hello, everyone. My name's Omar Zoni, and I'm going to be the MC for this event. First off, thank you all so much for attending. Nearly 1,000 people have signed up for this, so it's going to be a big crowd. Today, we're going to be discussing plastic part design, specifically how Solidworks can help bridge the gap between part design and manufacturing. To achieve this, we really have an all-star group of presenters, which is going to make my job as MC a lot easier. That being said, let me give you a brief introduction of the presenters and go over a couple of housekeeping items. Our first presenter is going to be Andy Routsis. Andy has over 30 years of plastic injection molding experience. He's an industry veteran. He really focuses on the injection molding training, and he's helped over 2,800 companies. Then we're going to switch gears, and Jesse Matola is going to be presenting. Jesse has over 15 years experience in plastic part design, and he's going to be showing us how to use Solidworks plastics to kind of optimize your overall design. And finally, Rick Reisterer is going to talk to us. And Rick is a business development expert. He's responsible for an almost 5x growth in the injection molding business at PCI. We also have a couple of in-house experts that are going to be answering the questions that you guys submit, and we'll go over exactly how to submit questions in a second. The first is Jeff Osmond. Jeff, can you turn on your webcam for a second, just so everyone can see your face? Perfect. So Jeff is a plastic injection molding expert. He did, I believe, an internship or an apprenticeship at an injection house, and we're very happy to have him as one of. I'm very happy to work with Jeff as one of my colleagues here, really supporting the Solidworks plastics product. We also have Sashi Sithambaram. Sashi, can you go ahead and turn your webcam on? Hey, Sashi. And Sashi is actually an overall expert on our Solidworks simulation software. And the two of them, along with myself and the people who are presenting, will be answering questions. Now, just a brief kind of overview of how this works. So there are a handful of us here that are going to be either presenting or I'm emceeing, answering questions. And then there are hundreds, or actually a few hundred people that are online watching this. And the way that you're going to ask questions is, hopefully you guys are seeing the video, right? There's a question dialog box inside of the GoToWebinar. You guys will ask your questions there. We're going to have 3 separate places where people can actually answer questions. So after each presenter presents, they're going to talk for about 15 minutes. Then we're going to have a brief Q&A for about 10 minutes and move on to the next presenter. And just so you guys get a feel for exactly where people are from, and we only focused on the US, there is an international feel to this. There are a handful of people in the Middle East. There are some people in Europe. I believe there were some people in Australia and the Far East. But you guys can see, as far as the US goes, this is where the hotspots are, where there are clusters of people basically. So you see a lot in California, the Northeast, a lot in the Midwest. Jeff used to live in Chicago, so Jeff knows there's a lot of industry there, and Sashi's in the Northeast, and I'm here in Southern California. So we have really good coverage from a SolidWorks standpoint with regard to plastics. So let me just take a quick minute here to introduce our first presenter, and that's going to be Andy Routsis. So Andy has over 30 years of experience in plastics training and consulting. He works as an adjunct professor at UMass Lowell, which is one of the the leading universities in the US with respect to plastic injection molding. He's owned a tooling shop, he's sold and rebuilt mold machines, and he's trained, again, over 2,800 companies in 37 countries on how to save resources and money by optimizing their injection molding process. So I am going to shut up now and turn this over to Andy. And Andy, I believe you're not using a webcam, so you can go ahead and start. I'm going to turn my mic off as well as my web.
Hi, everybody. Welcome today to today's presentation. I'm dividing this up into 2 parts. The first part is on initial material selection, and the second part is related to scientific molding and simulation. Just want to thank everybody for sponsoring this. DS SolidWorks, we enjoy working with them. They're our partner with respect to simulation. A little bit about our company. Currently, we have well over 120 online courses for plastics. We're always adding new courses to our stable of courses, as well as updating existing courses. We have 25 specific courses to part and tool design. And we have a store online where you can see how all of that is priced out. Now, before I get into this presentation, I want to make everybody aware of some very critical information here, because this is often overlooked. There are a lot of very important reference materials that can easily be obtained. In fact, what I've done is I've put together a whole grouping of these materials, and after the presentation, we'll be sending you an email, and we'll give you a link where you can download those. And there are literally thousands of pages of these materials. But let me just chat a little bit about them. Some of those are part design guides. Others are processing guides, guides on mold-based and steel guides, so you understand that a little better. Part and mold design books, information on how to get those, as well as technical service bulletins. I bring up this last one in particular, technical service bulletins, because what I found is most people aren't even aware that these exist. If you're looking to design or modify existing product, or you're having an issue somewhere, my suggestion always is to consult with the raw material supplier or material distributor, because they put together a number of these technical service bulletins, and I find them quite useful. In fact, some of these will actually compare their products to other products, or their plastic materials to other plastic materials, as well as their own competitors. And they can help you with things like snap fits, press fits, using inserts, anything of that nature. And this is all easily obtainable. You just have to ask for it. That's really the bottom line. So let's first talk about how we initially select a plastic material that you're considering. Well, first of all, you need to determine if it's a variable property. What we mean by a variable property, something like tensile strength, flex strength, impact strength. Those are the kinds of things that are what we term in variable. Now, you can influence those quite a bit by part design, and that's the key. You can find information on mechanical properties online, and probably the two most common online databases would be IDES.com, which is Underwriters Lab or UL Prospectors website, as well as another website called MatWeb, MATWEB.com, and you can get some basic information about that. And there you'll find things like tensile strength, flex modulus, impact, etc. So what you will find is that you can influence the plastic parts performance just by design. So things like adding a rib, or coring out an area, or increasing a boss, or adding a gusset, what have you. You can do all of that. Then we have what we call fixed properties. These are things that you can't change by design. So this would be something like a chemical property. So for example, you might have a part like polycarbonate that has fantastic impact strength, but if you throw some acetone on it, it's going to disintegrate. So that's the kind of thing that you have to identify up front. So what you should do is first start making a list of some specific properties that you're looking for, and write those down. So if it's chemical resistance, thermal expansion, that sort of thing, determine if these are fixed or if they are not fixed. That's really the key to designing a plastic part. And what you're going to find is this: you're going to have several choices. Today, there are more choices than ever. In fact, you'll see when you go online, it's a virtual drugstore. They literally will make up a material. But part of my discussion with you today is to try to stay with standardized materials and try to categorize them into their plastic families. And this is why we say limit your selection to 3 to 6 materials or families of plastics. And I'll give you a quick example of that in a moment. So when you initially choose these materials, again, determine what can be fixed and what can't be fixed, all right? And again, narrow it down. Now, again, within the Solidworks platform, you'll see 4,000 materials in there. You'll also see when you look online at MatWeb or UL Prospector, you'll see well over 100,000 materials. I think that the number is now close to 250,000. It's gone up quite a bit. But if you look at this example I'm showing right here, here's a part right here. It's the bottom of a hose nozzle for a garden nozzle. And that something that cannot be fixed on the thread design, where that thing has to screw into. So that's something that cannot be changed. However, you can change the design of the ribs that are outside of it. You can change the texture of the outside of it. There are a lot of things that you can do that would enhance the properties of this plastic part, but this is what you have to do first. You've got to first kind of write down your wish list and then prioritize it. And then when we start looking at these materials, and in this example, we'll look at three. For this particular part, we'll look at polypropylene, polyethylene, and nylon. And basically, when I use any one of these materials, I can vary the thickness, the ribbing, the gussets, anything I want at all on this that will affect the final design. So what I do is I basically create a simple comparison chart. You can see that on the right, where I've got high density polyethylene, polypropylene, and nylon, and I rate them on a scale of 1 to 10, and how much of a priority it is to me. So you can see at the bottom, I've totaled it out. And what you might find very interesting is, hey, nylon, that's the most expensive, but it buys me all of these other packages. So I need to make a decision on which way that I choose to go. So basically, prioritize what exactly you're looking to do. Okay, and again, quantify this as much as possible. So come up with your own values. So for example, if it's a garden hose, find out how much force it's going to take before you would actually break the nozzle as you're screwing it onto the hose fitting. If you've got to drop it from a 6 or 8 foot height, drop it to see how the impact is going to affect it. And this will help influence and help you prioritize your material selections. Now, the second part of this presentation is going to talk about scientific molding and simulation, just to kind of give you an idea. Now, one of the key points that I want to bring out is this. In this business, everybody tends to look at things through their own lens, through their own perspective. So, for example, a material supplier will try to fix or identify problems using a material, by altering the material, the way it's blended, the way it's compounded, what additive packages it has, etc. A part designer will try to modify or correct things, changing things like ribbing, etc. A mold designer will look at how's this going to fit into the tool, where am I going to part it, things like that. So my point of telling you all of this is that everybody is always looking at it through their perspective. So keep that in mind, all right? And try to look at other people's perspective, because they could probably identify issues that you may not have even considered. All right, now with scientific molding, it's actually a pretty straightforward process. Now, first, let me talk about why we call it scientific molding. We call it scientific molding because you can make the same part every time. Now, the way we explain that is this. If I had a photograph and I wanted to make a number of prints to distribute it to everybody, every one of those prints would be identical. However, if I had a painting and I made another painting and another painting, what's going to happen is each of those replications is going to be different. So by embracing and utilizing scientific injection molding principles, you will ensure yourself of a more successful and repeatable part. And that's exactly what you're looking to do. So with that, we try to minimize any variability during our process. So we try to use one speed when we inject into the mold. We look at how we're controlling that viscosity. If you look at that chart on the right, we're just showing you what happens as we start increasing the speed. You'll notice how everything sort of stabilizes as we get to the right-hand side of that curve. All right. Now, to know that we have set that speed up properly, in practice, what we do is we set up a series of short shots. So we short all the cavities so that we understand where that speed should be set, okay? How do we check it? Well, we check it simply by checking the weight. So reality is we should be 90 to 95% of the total part weight during first stage injection, all right? And it's important to realize the difference between an input and an output. An input is something you punch into the machine. An output is the result, all right? So we want to make sure we can differentiate that. Here's where simulation can help. you can simulate and look at what a part looks like at about 90% full, just to see where it's going. And you want to determine if just one speed can be used. You'd like to perform a rheology curve, because that is certainly going to help and understand how things stabilize. And with this, you can determine what the optimal fill time is going to be. And you can see this quite easily with simulation. Now, probably the most important thing you can do with simulation is that you can determine the gate and location. The gate and location are the two most critical things, gate type and gate location, on any injection molded plastic part. And I'm going to go through a bunch of those in just a moment, just to show you what we have available to us. It's also a good idea to get some other people involved so that they can give you their feedback on how things follow into their realm of things. Now, I'm just going to run through some typical gates. This is a sprue gate. You'll notice we've gated directly onto the part. This is the edge gate. This is the most common kind of gate that we have, and you have to manually degate it. This is called a flash gate. You'll notice how across the top it can distribute the material quite uniformly. This is a fan gate, and that fan gate can be expanded to the entire length of the part, so that can all be adjusted. This is a disc gate. This is typically what you see in a CD or a DVD. This is a spoke or picture frame gate. This is a ring gate. These are pin gates, and they're self-degating because the weight of the part will drop those parts off and cause the parts to detach from the gate. This is a pinpoint gate that's typically found on a 3-plate mold. This is a submarine gate, which again is a self-degating and the most popular gate as far as self-degating gates. This is another version of it called a cashew gate, because it actually just moves where you're putting the injection point is. And then of course we have hot runners, okay? In a standard hot runner, you gate on top of a round part. Is an example of a valve gate where that pin moves back and fills the part. Now, venting is another area that's commonly not understood, and that is this. You can never over-vent. The simulation software will show you all the critical areas where you must vent, and this is very important. So again, weld lines are very important to us. We always need to see where flow fronts meet and where they stop, okay? If a head-on or straight-on melt format will turn around and be the weakest area. So what we try to do is we try to create what we call the meld line, whereby you have two flow fronts that are going together, they're running in parallel, as you can see on the left. Okay. Now, the second thing we have is we call second stage packing. This completes the mold filling. This completes the last 5 to 10%. Okay, and this will compensate for shrinkage because all plastics will shrink. All right. And here's where we need to determine maximum minimum pressure, and we tend to run the process in the middle of this, but it's important that we establish that. And what's important is this: we'd like to determine packing time versus packing weight. If you look at the right-hand side of that curve, you'll notice how things level out. We want to see that point. You can see between 5 and 6 seconds where we've got this transition. That's where we're going from the material flowing into the gate, flowing out of the gate. Simulation also helps us with determining packing time and the tonnage requirements so we don't flash the part. Now, as far as filling a part, it's good to fill a part from the thick section to the thin section. Obviously, in any plastic part, the more consistent that you can be with part thickness, the better. Part cooling is also very important because it takes up an enormous amount of the cycle time. And this is where we transfer a hot polymer to a cold mold. Okay, typically we use water, oil, or steam, and we can adjust that. Again, we want to see what the output is of that. So we'd like to always determine the minimum cooling time. And again, this can be determined easily through simulation. And also we can determine a full optimal. Steel safe is a condition for any dimension that needs to be spot on. Typically, the best steel safe dimensions are in the direction of flow of the material. Those will be consistent, and typically what you'll find is your dimensions will tend to stay the same. As a rule of thumb, a lower temperature will equal a larger part, and a lower time will equal a smaller part. So this gives us better cycle time and better quality on the part. So again, we always need to watch out for transitions, because if you have a sharp transition, you're going to warp your part. All right, sharp corners will also warp a part. A thickness variation will warp a part. And so it's a good idea to model cooling lines. Also address any hot spots. Screw recovery is important. We want to have a consistent temperature whenever we mold. And it's a good idea to simulate and recommend a melt temperature when you're doing your simulation. And lastly is part removal. Ejector pins are the most common, ejector sleeves, ejector blades, lifters, you're moving more steel around. Stripper plate is the most uniform type of part ejection that we have. And air poppet valves, they use either to pop a part off of a mold or to assist in another type of ejection. And now with many parts, it's becoming automated. We're incorporating robotics. Again, slides are used to remove undercuts, core pins to do the same, lifters to do internal undercuts. Unscrewing cores are used typically for threads. Collapsible cores are used for threads or external details that have to be moved away for the part to get out. Expandable cores, again, will help move the part away. So these are just some examples. You can model all of that in simulations. But again, this is going to be a trade-off. So you're going to have to determine cooling lines versus how much steel movement that you have. Now, I just want to wrap up some of the key things. Please always add draft and radii to any part that you're modeling and incorporate this into your design. Okay, anyways, that wraps up my portion of this. And I'm going to hand this off to the next presenter.
Thanks, Andy. So before we go to the next presenter, we're actually going to answer a couple questions. And Andy, the questions actually are for you. So first of all, when, in your opinion, when should you consider using simulation software? And that's for Andy Routsis.
Okay, so that's a great question. When should you consider using simulation? Well, basically after the initial concept or model is complete and you have established that it's moldable. So that's the short answer to that.
Okay. Another question for you, Andy. What do you see as being the most common mistakes using simulation software?
Probably the biggest is they tend to want to use simulation after there's a problem, so they don't use it initially. So they get themselves into trouble to begin with. And then the other big part of it is they don't understand enough about molding. You know, even fundamental knowledge will help to interpret what, you know, the software is actually telling them, because the software is giving a lot of good information, but if they haven't got enough fundamental knowledge, that can become an issue. And also with the software, they should play with it a little bit. Try filling the part at 25%, 30%, 50%, 90%, so you can see exactly what's happening as that mold is being filled, because that can tell you a lot of what to expect with the part. So don't be afraid to experiment.
Great. Yeah, I mean, we hear in the simulation space in general, we hear a lot of times garbage in, garbage out, right? So it's the same for plastics, right? You really have to understand your inputs, which you pointed out. We have another question for you, Andy. For stage 2 pack, do you prefer running on pressure or velocity to your hold point, since pressure is variable and velocity can be constant?
Pressure usually set at the same stage, at the same value as first stage. That's probably the most common.
Okay, thanks for that. So we're going to move on now to the next presenter, and the next presenter is actually Jesse Matola. So Jesse, again, he's a plastics professional with over 13 years of industry experience, covering processing, part design, and product development. Jesse is a graduate of Penn State University, which is another great plastic injection molding school here in the US, and has spent the majority of his career working on relatively large plastic part products. So Jesse, if you want to go ahead and get started and turn your webcam on. Jesse's actually going to be showing an overview of the software. So,
yes, thank you for the introduction. And Andy, what a great start to the webinar. A lot of great information there. And what I'm planning to do is piggyback on the topics Andy discussed and try to contribute to the verbiage that he spoke about, and showing everybody on the webinar where those features are in the analysis. So I have 2 parts that I did a full analysis on: fill, pack, cool, and warp. And what we'll look at is in each of the boundary conditions, the settings that you're able to adjust to tweak your design or your outputs whenever you're getting your result. So it's an important thing to understand too, that there's two ways to work with simulation. You can be working on the front end with design, and you're taking more of an iterative approach. You'll do multiple flow analyses, and then you'll go into pack and cool, and then you'll warp, you'll have design iterations. Or you may come from the other side of, you are working with an existing part, you have an existing mold, you happen to have the CAD file for the tool, which would be good, and the part. You can work backwards, in which case you would be doing all of those simulations at one time: fill, pack, cool, and warp, as opposed to the forward iterative way. So I'm going to turn my camera off right now and go into the simulation. So what we have here is a simple case, that a simple box with some ribs underneath of it, and you can see a flow, pack, cool, and warp analysis was done. And just to jump into a couple of the things you might want to look at whenever you're doing a simulation is obviously your fill time. Everybody likes to see how the flow path goes. It's definitely a good selling tool and a good way to convince customers of any issues you're having with tools whenever you're working from the manufacturing side of it. So when you're beginning from the design stage, you'll be evaluating knit lines, gas traps, and where the part is flowing, and any additional concerns you might have that deal with the flow path. You'll look at the pressure to fill it, and you'll sometimes look at the bulk temperature at the end of fill. Your volumetric shrinkage is always something good to look at as well, because you'll see where the part's going to be shrinking the most, and where you might expect to see your volumetric shrinkage turn into influencing warpage. Cooling time being another. Let me hide that. So I just set the defaults on these. So right now it's saying 50 seconds. Whenever you set up your simulation, you can specify a cooling time, or you can just let it do what it wants to do. You can tell by the volumetric shrinkage when the actual gate seals off, and how much cooling time you actually need. So looking at pack for a little bit, bringing up the results. Let's try skipping over to cool. Whenever you're starting your cooling lines with your part, you can start with a sketch or a solid body, and that way you can actually create conformal cooling by way of your sketch. It's a little bit more complicated to do it that way. You can see here it's just a simple series circuit that is going back and forth across the part, one in, one out, but you still are able to model it the way you want so that you can get optimal cooling. And there's, the books that Andy mentioned are great references. There's always considerations to take into account of where you need to eject the part, what cooling you need to have in certain areas. So there's the simulation software is not just a standalone. It's always good to have book resources, as well as any personal human resources that you have in your departments. So things like the cycled average mold temperature are a good thing to look at. You can do a clipping plane on it, and you can see where the hot spots are on your tool, and you can actually go in and measure to see what the difference is in those different areas. So you can go from there, click on this next one, and see what the difference in mold temperature is with this given configuration cooling layout, and your tool steels and everything like that. So let's try going back to the packing. And again, I'll show the runner here while that's loading up. You can also, there's 3 ways to design your runner in SolidWorks simulation, plastic simulation. You can create a sketch where you will assign entities and diameters and segments to it and create a generic representation of your runner. You can model it in 3D and get your runner exactly the way you intend it to be. Then there's a third option, the runner design wizard, where you have 3 different options of creating a runner that you don't need any sketching for. It's all in the menu system, where you can enter in your diameters and lengths and thicknesses, and it will create either what you see here, a cashew gate, it can do a tab gate, and it can also do a tunnel gate. So if I get through all of these 2 samples, I will go into setting up an analysis. But I figured this was more valuable to everybody after seeing Andy's presentation. So I apologize, the pack isn't opening up. So this is the warpage analysis that it was created. So you can look at the warpage in the different directions and what you can expect the part to warp in different directions. You'll commonly want to look at the total warpage, and then you can actually, because it's sometimes hard to actually tell how much it's warping whenever you're looking at it on a printout or on a screen, you can give it a deformation scale. So you can exaggerate it whenever you're looking at the analyses. And there's obviously other outputs here that you can look at that are maybe relevant to your part. Always sync mark profile, you'll get a nice representation of where you can expect sinks to be, and also if you look up here, what that approximate value might be. So in this case, I intentionally made the ribs to violate the standard of the rib design principles so that it would create somewhat of a sink in this area. So getting into some of the set points, as Andy mentioned, there's always a plethora of polymers, coolants, and mold materials that you can choose from, and SolidWorks does have an excellent database of those to choose from. So one of the first items I'd like to touch on that Andy spoke of was the fill settings. So whenever you go into the fill settings and set up your analyses, you can set your cycle time, you can manipulate your melt temperatures and your mold temperatures. Your injection pressure limit is important to make sure you set it high enough whenever you're running your analyses so that you don't go pressure limited, and as well as your clamp force. Whenever you're creating your fill settings, if you plan on doing a pack analysis, and Andy spoke of this, if you can fill 100%, but you'd basically be packing out 100% full part. So if you wanted to perform a 2-stage or a scientific molding, you would back this down so that whenever your packing analysis kicks in, it would start off at the 98% full as opposed to 100% full. You can also change your flow rate settings right here. So again, this was just the default, and you can control by volume. So this would be valuable whenever you're working backwards. You have an existing machine and tool. You have all of the parameters. You can use your screw position. You can use the volume or your screw diameter up here. Sorry, your screw position, your volume, and the flow rate, your maximum flow rate of your machine. And then you enter those values in. If you have multiple positions or stages that you're doing, you can enter that in, and you can replicate your existing process to find out if the simulation is giving you exactly what you see in the real world. That way you can make any changes necessary to make the simulation fit the real world. And then if you're trying to solve a problem, you can go forward from that point. So again, Andy spoke of one fill setting. If you wanted to have just one fill setting, it's good to have two because it starts off with one. You can have this real low, and then this would be at your maximum fill time that you set. If you're going to be doing a warp analysis, you need to set your gravity downward direction, which is right here. And you'll reference your triad right here to understand which direction you need to put. So you have also your machine database, which is very helpful. I used it a few times when I was working on a contract job, finding their machine and making sure that because often you can get a mismatch of machines and barrels and clamps on machines that have been purchased secondhand. So you can use this to make sure your machine that you're dealing with is actually giving you the values you want by looking at the screw diameter, shot volume, etc. that you have here. Pretty good list of machines that they have here. So the next thing we can get into is, and venting. You can look at the venting analysis here as well. Andy spoke of this. So you can set an initial cavity air pressure and the internal temperature. So moving on to the pack settings. At this stage, you'll set when you're setting up your analysis, you'll set your holding time and your cooling time, or you can leave it at default. Here is where you can set a packing profile. And again, if you have the machine information, you can work backwards with it, or if you know what machine you're going to be using, you can use that information. A good place to start is just the relative to injection pressure. It's not the best. It's not what you want to set a process off of, but it's a good start. Then getting into warp settings, all you'll set here is your ambient temperature. So this would be the temperature that the part is going to see once it's ejected from the tool. And again, it wants to know what the gravity downward direction is. In this case, when it's sitting flat on the table, the negative Y is the gravity direction acting on it. For your cool settings, a lot of set points you can manipulate here. You can change your melt temperature as well, your coolant temperature, and your flow rate, as well as your mold open time. So whenever you can, again, speaking from working backwards on it, if you have multiple cooling lines and you're having a problem with a hotspot, you can model the cooling lines if you have the mold drawings or the 3D CAD file, and you can put a lower flow rate on those cooling lines and simulate the hotspots you're getting, and you can have a good idea of what's happening there and what you need to do to fix that problem. So for injection locations, a good way to start is right here with the automatically add locations. If I click it now, it's probably gonna pop onto the runner, but if you use this before you have a runner on it, it's going to find an approximate center of volume of your part, which is not always, you might not always be able to gate in that location, but it'll give you a good starting point of where you might want to put your gate. So whenever you're adding once you have your gate location added, you can select additional faces of the elements that it's attaching to. And if you happen to have multiple gates, this is where you would set the control valve. So you would decide what material is coming through it and when it turns on and off during the cycle. Going down the list, you have 4 options for your coolant flow. mold wall temperature being the fastest solving and coolant flow field being the most extensive on your system for trying to solve it. The mold wall temperature doesn't take into account any fluid flow, but these top three do. So as you're starting out with your analyses, if you don't do the cool settings analysis, it's just going to assume a uniform wall temperature, which isn't always the case. So just like you saw before when I went to the mold view of the mold average cycle, temperature, you could see where the hotspots were in the virtual mold that is built around this. So whenever if you create your runner and your cooling lines when you're meshing the model, it will automatically identify things like the runner element and what the cooling lines are. If you mold them solid, if you build them in solid, whenever you're doing your meshing, you have to select those domains individually and assign them what they are, because it might think that it's another body. So let's skip over to the other file. And this one, I wanted to jump back one step to before starting the analysis. One good thing to do is always to have a refinement circle, a mesh refinement circle here. That way you can, when you're doing your meshing, you can select that circle as well as these additional faces. And another thing good to do is when you're gating into a part like this, on a face, you'll want to mesh the underside of it. And I'm going to go back into the analysis and show why. It gives you a little bit more resolution when you want to take a measurement in that area. So let's go look at that. So we'll turn on our clipping plane and our mesh model. And hopefully everybody can see that. If I had not meshed the underside here, then I would have a resolution of what's represented out here, and I might not be able to get good temperatures here. So let's look at what some of the temperatures might be. So cooling average temperature, part cooling time. It really gives you a good representation of what the part's going to be doing and how you need to design your part and mold together so that you succeed in your speed, cost, and quality of your part design and your manufacturing. So there's a lot more results that we can get into with more time, and I'm sure there's other webinars and tutorials that explain it better than I could right now. So I hope that I am giving everybody a good taste of what the program can do for you and how it can help you break into the simulation realm. Again, I wanted to reiterate as a final thought, SolidWorks Plastics is a useful tool during the development phase, but one should also follow up and duplicate the actual process in the software to check your results for future analyses. So that's my current job now, working with a third-party molder. We're not only doing front-end analysis of the fill and the cooling for the mold design, but we also have existing tools that need analyzed. And when we get the tool back on those new designs, I intend to run the analysis on that and compare it to the actual physical machine settings that our process engineer sets up.
Jesse, thanks a lot. That was really great. Thanks for showing those two models, and hopefully the people in the audience were able to kind of correlate some of the stuff you were showing back to what Andy talked about. So we have a lot of questions. Guys, keep submitting your questions, even if we don't answer them during the event today. The internal team is going to go back and actually will respond to your questions. So definitely submit questions. So the first question, Sashi, how do you, and if you want to go ahead and turn on your webcam, Sashi, how do you determine the draft on a part?
Hey, Omar. Yeah, that's a great question. Every part is unique. There's no one angle for a plastic part. For example, a thin wall at high pressure requires more draft than a thin wall at low pressure, right? So ideally, you want to have the most draft possible that makes sense for a cost perspective, form, and functionality. So just to throw out some numbers, in most cases between 0.5 degrees for a vertical face, between 1 to 2 degrees for all other faces is typically enough. And between 3 to 5 would be even better. Again, depending on the part tolerance. Some requirements for shutoffs, you have to have at least 3 degrees. Light textures, you should have 3 degrees. For heavy textures, it is recommended to have 5 degrees or more. So a last note to that is if you have a part that can't or a face that can't even handle 1 degree, then specifying any draft, right, even half degree, quarter degree, would be better than not having any draft at all.
Perfect. Thanks, Ashley. So the next question, I'll answer this one. The user asked, hey, I'm running SolidWorks Plastic Standard. Are most or all of what Jesse is showing available in plastic? I'm assuming you mean plastic standard. So Jesse actually was nice enough to show capabilities across all 3 plastic products, so standard, professional, and premium. The best way to figure out if what he's showing is something that you have, if it's a capability that you have within SolidWorks Plastic Standard, is to probably reach out to your reseller or just take a look. For instance, warping and cooling are things that are not going to be available to you in Plastic Standard. Plastic Standard is really just meant to give you the fill of a part and what it's going to look like when it fills, where weld lines are going to occur, air traps, things like that. The third question, and Jeff Osmond is going to answer this one. So Jeff, if you want to pull up your screen, what is the benefit, or your webcam, sorry, what is the benefit of using the runner wizard? Is it more accurate than modeling it in 3D? Great question.
It's not so much accurate. I believe it was brought up once before that you don't have to start with sketch lines. You can basically real quickly put down some runners, even the sprue and gates down fairly quickly. Now, a side benefit of that is, let's say you're working with a family mold and you're trying to see if it's a balanced mold. One part's bigger than the other. When you use the runner wizard, then you can use the balanced runner system, and it goes through and tells you what sizes the runner needs to be to balance out that mold.
Perfect. Question 4, this is for Andy Routsis. In general, should a rectangular part be gated from an end or from a side? Another good question.
Yeah, in general, you want to gate a rectangular part from an end. Now, the example that Jesse was showing, again, it's more of a container lid where you didn't have anything but ribs or any kind of cores or cutouts. So, and the trade-off actually is this: if I gate it on the end, it's going to grow a bigger mold base. If I gate it as Jesse was showing in one of his drawings, again, it's going to have a smaller mold base than gated in the top center. So typically, if that were a cylindrical cover or a rectangular cover, you would gate where Jesse was showing. But if that were a connector, or if that part had a lot of core outs, you probably want to consider gating more on an end. The beauty of the simulation software is you can move that gate around. You can see exactly what's going to happen. But just so you know, by default, the simulation software is going to look for the shortest stuff, flow length. That's what it tends to look for.
If you do the automatic gating, you mean?
Correct.
Okay. And so we're going to answer at least 2 more questions. Well, at least the next 2. The next 2 are going to be, again, for Jeff. First one, Jeff, will there be a difference in cooling between a textured and a non-textured cavity and core in a mold?
Not really. On the simulation side, what you're looking for is the distance from where the cooling line is to the actual wall. Really, the texturing isn't going to make that much of a difference unless it's very deep knurling But even then, it's not going to be that far off.
Okay, great. Next question again for you, Jeff. Are there default process parameters built into SolidWorks for each resin, or do they all have to be manually entered from the resin supplier's data sheet?
No, they are automatically added in. Things like mold temperature, melt temperatures, but you have the ability to go on the fly and change that. So when you go in and you're running a study or just about to run a study, you can go into the fill section and you can alter the mold melt temperatures. Now you don't want to go crazy with altering melt temperatures, then you're gonna degrade the material if you start moving those around. But the mold you can definitely be very creative with to achieve what you're trying to achieve.
So you can modify a lot of those inputs.
Yes, on the fly, but they do come with the material supplier.
Right. Okay, at least one more question, and this one is for Sashi. So Sashi, how can design engineers use this software if they don't work for an injection molding shop, especially since they don't know a supplier's parameters? Again, these are great questions, guys. Thanks.
Yeah, that's a great question. So I think Jesse kind of put it really well earlier, right? He's a designer, but using a injection molding house to produce the part. So as a design engineer, using a simulation software like SolidWorks Plastics gives you more control over that process, over that going that back and forth. So if you think about in the past of having to rework your mold, or having to change a gate location, or to change certain plastic part geometry due to maybe well lines or race tracking issues. Now you'll be able to predict all that early on within the software. Now to address the part suppliers or the material supplying, within SolidWorks Plastics itself, we have over 5,000 materials. And a lot of times the suppliers do have material properties. They might not have it out on the internet. So if you reach out to them directly, they might be able to share that parameters with you. So if a last case is if you cannot find the material property from the supplier, you can even use a material property that's close to what you're plan on using from the database that we have. Again, we have over 5,000 materials in that database.
Perfect. Thanks, Sashi. I think that now we are going to move on to our final presenter. And the final presenter is Rick Reisterer. And Rick is he's a seasoned professional who's responsible for business development at PCI Plastic Components. And I believe he's had that role since around 2005. When Rick joined the business, their revenue was about $7.5 million. Since then, it's grown to about 34 million. And PCI has won multiple awards, including, I think for a handful of years, they were rated the best places to work in the plastics industry. They've won Sustained Excellence Award, Wisconsin Manufacturer of the Year Award. I think there was a local Milwaukee award that they won. They've won multiple patents. So we're very happy to have Rick here presenting to talk to us. And Rick, I'm going to shut off my webcam and turn it over to you. Thank you very much.
Well, it's great to be here. I'd love to take credit for that growth on my own, but part of the discussion point that we are going to talk today is working with strategic partners, of which we consider SolidWorks a strategic partner of ours to assist us with our growth, but more importantly, to assist our customers with their growth. So that's really what we want to talk about. First of all, thank you, Andy and Jesse. I could tell you I'm a little bit intimidated with all the detail that they're talking about, but we'll give this a shot. I first wanted to start out by, I don't know if anybody remembers this TV show, but it was 98 episodes of the finest TV known to man. But really what we're trying to say here is there are people out in the marketplace to support us and help us. We are not SolidWorks experts, but we have SolidWorks folks that are here to help us. And it has always been the mantra of PCI is to not be out on an island on our own, but to utilize the experts in their specific field. So what do I mean by that? We develop strategic collaborative relationships with our vendors and with our customers. Those include for us resin suppliers, tool vendors, RJG process control suppliers,
automation experts, press and support equipment manufacturers, and the list goes on. And you can see SolidWorks, and then of course our value-added reseller GSC right here in Germantown. We believe are all a part of our team. We owe it to our customers to bring in the best of of these particular applications, and that's what we've essentially done here. It was funny, the other day somebody asked me, well, what does strategic and collaborative relationship mean? So I want to highlight this. So I know I can't see a raise of hands on the number of people that are here, but most of us own one of these things, right? Well, if you're fortunate enough, you have this, which is children. So what I've decided to do is to develop a strategic and collaborative relationship with vendors and my children, because they're way smarter than me and my iPhone. That's the illustration that I wanted to give you as to what it means for us to partner up with our friends at SolidWorks and GSC. Why SolidWorks Plastics? We started investigating mold simulation change in about 2016. That was spearheaded by Kurt Barron, our engineering manager. And what we wanted to was to continue to expand our capabilities for our customers. Time to market, speed to market, and obviously doing it right the first time was becoming obviously more and more important. And so we went out and we evaluated 4 leading vendors, and we were looking for accuracy. I think Jesse mentioned that one of the things that you need to do is, number one, run it through your simulation software and then compare it to real life components. That's actually how we chose the software that we did, is we had parts that we knew were doing things that we probably could have predicted had we had the software ahead of time. And that's how we developed the accuracy side of it. Functionality, the output that we were going to get, obviously ease of use, and then the support. All 4 of these are, quite frankly, excellent tools, if you use them properly. What stood out for us is DS SolidWorks and GSC and our philosophies of how we do business and how we go to market and how we support our customers completely aligned. And that really became the final factor for us. And quite frankly, we made one request of SolidWorks and GSC, and that was to challenge us. The worst thing in the world that we could have had is went out and spent the money on this software and not make it dance. So we challenged them to challenge us weekly, monthly, daily, to utilize this software and not have it be the typical treadmill that sits in the corner 1 week after you purchase it. And that is what they have done for us. How has it changed what we're doing with our customers? We utilize it on all of our new part launches. Andy mentioned it and Jesse mentioned it. We're doing this ahead of time before we're cutting steel. We're sharing that information with our customers and their engineering teams so we can all make appropriate decisions on how we're going to cut steel, where we're going to gate, and what are the potential pitfalls of the design and how do we work our way around that. It's incorporated as part of all of our new part launch processes. And it's going to continue to play a significant role in our new product development. Everybody knows parts are getting more complex. There's a lot more metal to plastic conversions. Materials are getting more complex, more fillers, more glass. And so as those things get more complex, we need to keep up with the times with the science and physics behind it versus tribal knowledge. And reduce costs and reduce time to market. One of our mottos has always been, there's a better way to do it, find it. The days of pushing buttons and hoping that you're going to produce a good part are over. There's science behind it. Andy was talking about that. Jesse was talking about it. There's physics, there's technology, and there's automation. And that is the reason that we have gone down the route with all of our friends at SolidWorks and GSC. But what does it all mean? Here's really where it counts in the bottom line. One of my favorite books is Hope is Not a Strategy by Rick Page. And what we did is we tried to quantify what this means to try and do it right up front. And we call that reducing the number of round trips. And we define the round trip as you're sampling, you're measuring, you're modifying the mold, you're sampling, you're measuring, you're modifying the mold, ... I think everybody gets the picture. And just a rough estimate, we perform an analysis of what a round trip costs. And the very basic level we determined was about $2,500 per round trip with about 1 to 2 weeks of lost time. Note, this does not include the mold adjustment costs themselves. This is just simply time that we are trying to quantify. Well, what does that mean? The example is if we do 100 tools per year and each one has 2 round trips, that's about $500,000 of lost revenue, as well as 200 to 400 weeks of lost time. And that doesn't even begin to define the loss of goodwill with our customers. So it was incumbent upon us to continue to search out technology, search out automation, but not expect that we are going to be the experts at it, which is the reason why we landed with Solidworks and GSC. Going back to the don't be on an island, here's basically what where we feel we are at with our friends. These are the team members that have helped us through it from GSC and Solidworks. And this really has helped us take this to the next level. And we got a lot to learn. We see these guys weekly, every other week. They're in our office helping us get better. And that's the objective. So again, the bottom line for us is the motto of there's always a better way to do it, find it. We have a passion for challenging the status quo. It's expected for us to continue to get better. That's what our customers demand from us. And that's the direction that we're going to continue to move.
Thanks,
So,
Rick. Thank
sure.
you for that. That was great. So I believe that we're going to have another round of questions, guys. Keep submitting your questions. I promise that we'll get to as many as we can. First question, actually, the first two questions are going to be for Jesse. So, Jesse, in the demo that you just gave, the person wants to know, are they to assume that the feed system was based on beam elements? It was alluded to that they can be modeled as TETs as well. So, nope.
So yes, whenever you create your cooling elements or runner elements from a sketch, I believe you are creating beam elements, and that's how it's solving. If you were to model your runner or your cooling line with 3D geometry, you would then have the option to either mesh it with tetrahedral or hybrid tetrahedral, and there's a couple other meshing options as well that you could use with it.
Perfect, thanks. Yeah, so the software actually gives you both options depending on what you want to do. And then Jesse, another question for you. Is there a recommended gate or process for a flat surface? Oops, sorry, my screen just moved a little bit. Is there a recommended gate or process for a flat surface that will leave the smallest blemish behind?
If the flat part of the question is the critical factor, then you have to decide what your gate location is, and you have to make sure that you're not inducing any undue stress by a small gate. So it's always a balance in plastics. You put a gate where you can so that it's not visible, or you make it large enough so that you don't over shear your material. So you can make a very small gate, but there are trade-offs to that. If you can exceed your shear rates during filling for a very short amount of time and not suffer any problems, but it's good to try to not over shear your material. So the direct answer is that with the simulation software, you have the ability to run quick analyses and determine if your part's going to warp, if number one, if you're going to over shear your material in the gate, number two, if your part's going to warp with the pressures that you need to fill through that gate.
And by over shearing the material at the gate, does that cause a degradation in the quality of the material?
Yes, it can vary anywhere from a cosmetic blemish called gate blush, which looks like anywhere from a halo or a cylinder, sorry, a disc of splay surrounding the gate, to if it's too high, it could cause structural quality problems.
Wow. All right, Jesse, you're on the hook for a couple more. It looks like people were really interested in your demo. So this question is, I'm new to injection molding and I don't use SolidWorks yet. Seems to me this simulation is more for manufacturers. If I were to draw a plastic product in SolidWorks, could I then send the drawing to someone else for simulation? I'm assuming they could probably send it to you, Jesse.
Yeah, it's possible. I don't know if that's a conflict, but yes, you can send it out to simulation companies. That there are plenty of design houses and simulation houses that specialize in that and can turn that around quickly. The great thing about SolidWorks Plastics is because it's embedded in SolidWorks, it is such a useful program for designers to manufacturers, because even in a manufacturing environment, if you have SolidWorks and you're building fixtures or tools or something like that, and you happen to be an injection molding facility too, you can add this program on and start running analyses to start solving problems in that realm too. So it's designers to manufacturers and any applicable situation in between.
Great. One more, at least one more for you, Jesse. I would like to get, so here's the question. I would like to get in touch with a plastic injection molding manufacturer to manufacture a plastic ruler I have a patent on. Do you know how I could get a list of some plastic injection molding manufacturers?
I think I could help you there with where I'm working, but you can always just do your Google search or go through the industry literature of who the manufacturers are. That you can Google it easily and find out what's in your area. But SolidWorks, I saw it debuted at SolidWorks World. Is they have a vendor. Somebody jump in and correct me what the name is, but you can submit your part through the SolidWorks portal, and approved vendors, SolidWorks vets the vendors and make sure that they're high quality. Right. And you can actually send your part out there and get bids and have somebody manufacture your part.
It's part of the 3D Experience Marketplace, actually. Yeah. So if people have questions about those, you can reach out to me. Although there are a couple of the guys who are presenting here who could probably also help. Let's move on to question number 5. Rick, this is an easy one. I could probably answer this one, but I'll let you do it. What does PCI stand for?
Plastic Components Incorporated. Okay.
Question 6, Jeff. This is a great question that we hear a lot. So you've run your plastic analysis, you've gotten a deformed part, that's warped. Can you actually deform that warped part back into SolidWorks to, add it to an assembly or run a finite element analysis on or something?
Yeah, you can go ahead and export that with a deform factor. So you can do plus or minus deform factor. A minus factor would actually give you what you should be cutting in the steel. So it's new functionality within SolidWorks 2018. And so basically, if you wanted to export that file, there's several different file types you can export to, and SolidWorks being one of them.
Perfect. I think that is where we're going to wrap up. So again, I want to thank everyone who's participated, a very engaged audience. If we didn't get to your question, we will do our best. We'll answer those questions. So we have a whole list of the questions. You'll probably be getting a personal response from either myself, Sashi, or Jeff.